Okay, so in this case it says the probability that someone has the disease is 1 in 10,000, and the probability that that if somebody has the disease, the probability of detecting the disease is 99% or 0.99, and if they don't have the disease, there's still a 2% chance that the test says positive. Okay. So overall, if somebody goes into the office, they get tested, and it comes back positive, what's the probability that this person carries the disease? That's what we're asking for here, okay? And the answer that I got, I just erased it, but okay, well, oh, I forget. Okay, I was gonna write this up, but we'll go through here. So we'll work this out, okay? So what's the probability that someone has the disease?
0.0001.
Yeah, so 3 zeros and a 1. Okay, so what's the probability that someone doesn't have a disease?
0.9999.
Okay, 0.9999. 9.
4
4 nines. 4 nines after the decimal. Okay. If they have the disease, what's the probability that the test shows positive?
0.99.
0.99. So 2 nines, and then that it shows negative?
0.01.
0.01. Okay, and then over here, if they don't have the disease, what's the probability that it tests positive?
0.02.
0.02, and over here?
0.98.
0.98. Okay. So, if someone tests positive, what's the probability that this person actually carries the disease? Let's figure out what's the probability that someone might test positive. Okay, there's 2 ways somebody can test positive. They have the disease and they test positive. So what's the overall probability that someone has the disease and tests positive?
0.00.
Okay, yeah, it's going to be 4 zeros, 99. Okay, and then over here it's like I hope that's right. 1, 2, 3, 4, 5, 6. Yeah. So 5 zeros and then a 1. Okay. And then over here, I got 4 nines times 0.02. So I get 0.019998. And over here, I get whatever. I don't need to do that. Okay. So overall, the probability that someone might test positive is there are those who have the disease and test positive, and there are those who don't have the disease but still test positive because their test isn't perfect. Okay, so overall the probability that someone tests positive, 0.0034 plus overall this is 0.020097. Okay, so look, just a tiny bit more than 2%. Okay, a tiny bit more than 2% will test positive. Okay. And the question is, if someone tests positive, what's the probability that this person actually carries the disease? Okay, so with this, what this says is that we are limiting ourselves only to those who test positive. So somebody has tested positive, they're either somebody who has the disease and tested positive, or somebody who doesn't have the disease and tested positive. Okay, so the answer to this is probability of disease given that somebody tested positive. So this is going to be the probability of disease and test positive divided by what's the probability that someone tests positive. So here on the top, we want to know what's the probability that someone has the disease and tested positive. So that's going to be 0.1234 4 zeros 99 divided by the overall probability of testing positive, 0.020097.
Where do you get the 0.020097 from?
I got that by adding this number,
Right.
the people who have the disease and tested positive,
That number.
and then this number,
Okay.
the people who don't have the disease and still tested positive. Yeah, so I get 0.00 4926. Okay, so I could round this off to just 0.005-ish, right? So that's about, and if we get this, this is actually equal to 1 in 203. 1 over 203 is equal to 0.004926. Yes?
When we do these problems, how many decimal points do you want to keep? Because I did have different numbers.
Yeah, you know, well, for a weird problem like this, okay, you're gonna have to keep a bunch of decimals because, I mean, if you kept less than 4 decimals here, you'd just be at 0, okay, and that would mess up all of your calculations. So, I mean, in this case, you know, just keep them all, just for this problem, okay? And in calculating some of the other numbers, maybe it doesn't matter as much, okay? So here it says, if somebody tests positive, what's the probability that they actually carried the disease? It's still only 1 in 200, okay, 1 in 203. So that seems like very small, and it seems very kind of counterintuitive. When you first read this problem, I think the initial feeling is that, oh, you tested positive for the disease, you probably carried the disease, okay? But it turns out somebody tested positive for the disease, it's still more likely that they don't have the disease. And the reason for that is that the disease is so rare that it's more likely that you are one of the false positives of the test than to actually be a disease carrier. Okay, that's what we've got going on. Okay, so that's what we have. So the other numbers in this thing, 0.0001. This is the answer that we were going for, 0.004926. And what is this number right here?
0.000099.
Huh? This one is just 0.99.
Oh.
If you have the disease, given somebody has the disease, what's the probability that they test positive? This is probability of positive given disease, 0.99. That's directly in the problem. Alright, is that okay? There is an example in the book, and I recommend that you follow the example along. As you do the reading in the book, a lot of times whenever you see numeric examples, I recommend taking a piece of paper out, kind of covering up the numbers, and see if you can do the actual problem. And then once you kind of move along, you can bring the paper down and see if your answers line up. Okay? Because if just by reading through, I think most of us, we're used to reading text, but not really reading numbers, and our brains don't really comprehend numbers super well when we just read them. So it's best when you actually punch them into a calculator or write the numbers out yourself, then you understand where those numbers are coming from. Okay, this is all right? Questions on this? Yes?
Well, this might be a stupid question, but I'm confused as to why for the givens, the given stuff is, I guess, throwing me off. So maybe once I read, I'll get it better. But the positive given disease.
Yeah. So this is basically saying, if somebody has the disease, what's the probability they test positive?
It's 99 or
Yeah.
0.99. But
And over here is if somebody tests positive, what's the probability that they carry the disease? So look at the part that comes after the vertical line and say, if I know this bit of information, what's the probability of the part in front of the line?
oh, okay, that
Okay.
helps.
So if I know the thing after the line, what's the probability of the thing in front of the line? And so maybe the general formula, I'll put this up here, is that anytime we have something, probability of A given B, this is equal to the probability of A and B divided by the probability of B.
Right.
Probability of A given B is equal to the probability of A and B divided by the probability of B. probability of B given A, this is the probability of A and B, or I can say B and A, just kind of divided by the probability of A. Okay, all I've done is I've just changed the letters, switched the place of the letters and switched everything there. And you should know that the probability of A and B is equal to the probability of B and A. So that doesn't matter. And this applies to all events, okay? So dependent or independent, it doesn't matter. This is always true. Okay? So if this is always true, I can then get another equation for the probability of A and B. So the probability of A and B is equal to, and I'm going to multiply both sides of this equation by the probability of B. And I'm going to get the probability of A given B times the probability of B. And likewise, I can flip all the letters around and get the exact same thing. And that's actually what we did right here. This is the probability of D. This is the probability of positive given D. And when I multiply those two together, I get this number, which is the probability of plus and D.
Can you go through that one more time?
Okay. So I'm just illustrating how what we did over here. So the probability of disease is 0.00, whatever, 3 zeros and a 1. The probability that someone tests positive given they have the disease is 0.99. Okay. So if I multiply this times this, which is basically this times this, I'm going to get the and part. And that's what I did get, indeed. This number, the 4 zeros and 99, is the probability that someone tests positive and has the disease. And that's what we have. Okay, so if events A and B are independent, what is the probability of A given B?
A times B? I mean, probability of A times.
Okay, well, before we get there, alright, so if A and B are independent, what's the probability of A and B?
Probability A times probability B.
This is the probability of A times the probability of B. Okay? This part's okay, right?
Mm-hmm.
We did this. Alright. So,
Probability of A plus probability of B for the infinite one?
no. So, if A and B are independent, the probability of A given B, okay, well, what do you notice here? I got the probability of A and B is equal to the probability of this thing times the probability of B. what we've got going on is that this is equal to the probability of A. If A and B are independent, the probability of A given B is just the probability of A. Alright? And let's think about what that means.
Oh.
It's, what does it mean to be independent? It means the outcome of one event has no influence on the outcome of the other event. Alright? So, the probability of A given B is just the probability of A. Knowing the outcome of B doesn't influence what this number could be. Alright? So, when we had the dependent example, and I said, oh, if I know it's raining, the probability that there's traffic goes up. Alright? On the other hand, let's think of, so those events are independent, right? Because the probability of traffic depends on whether or not it's raining. On the other hand, let's say I have two coins, and I'm going to flip one, okay? I flip this one, and it's landed heads, okay? What's the probability that this thing is going to land heads? It's still 0.5, okay? It doesn't matter what happened over here, okay? So the probability of this thing landing heads doesn't depend on this, it's just the probability of this landing heads, okay? You could tell me all about this coin and everything that this thing has done, but it doesn't affect my answer. My probability of A happening, of the coin landing heads, is just the probability that the coin lands heads, whether or not I know B. Okay? And so by using this substitution in for here, we end up getting this exact same thing here. Probability of A and B is the probability of A times the probability of B, or independent events. There's a few other notational things that you might see, okay? So let's say we have the probability of A, okay? What is the probability that A will not happen? What is the probability of not A? It's 1 minus the probability that A happens. Okay? So, if it's 99% chance that, I don't know, that something happens, there's a 1% chance that it doesn't. We call this the complement. With an E, as in complete. It completes it. So together A and not A form everything. That's the complete picture, okay? So sometimes we write probability of A prime. This is, or the probability of A complement with the C, and sometimes we just write probability not A. These are all the same concept there.
Will they toss us all during our assignment, or?
Yeah, you might see. I think the book uses this notation.
What's the first one?
It's like a prime.
Oh.
It's like a. Alright, there's a few problems in the book that use a table, and you have to answer questions based on the table. I think it's straightforward enough where I can just say, read this section in the book and you'll be fine. Alright? Yes?
What circumstance would you calculate in that A? Why would you
Oh, well, I mean, we did it in our thing, right? We said the probability that someone has the disease is 1 in 10,000. What's the probability that someone doesn't carry the disease?
Okay, so that would be a not A.
Yeah, that would be the not A,
Okay.
right? And you probably do this all the time, right? Okay, like, I can't think of a good example off the top of my head, but if something. There's also a section in the book on density curves, alright? We can deal with something called a numeric, a random variable, okay? And a random variable let's deal with random variables directly. Random variables are outcomes to random events, okay? But we assign, but there's numbers, okay? The outcomes are numbers. Okay, so it's the outcome of a random event, and the outcome is a number. So a random event could be something like I flip a coin, right? And the coin either lands heads or tails. That's a random event. Okay. I could easily change this into a random variable by saying I flip a coin, how many heads do I see? And the answer is either I see 0 heads or I see 1 head, right? It could be, so certain things lend themselves to random variables naturally, like we roll a die, what number shows up, it's going to be a numeric outcome, okay? It could also just be like, let's say I assign each of you a student ID, okay? I assign you guys a number, or I maybe I take a whole bunch of ping pong balls and I have you guys write your name on one of them, and we put them into a machine and we mix them up, and I draw a name out, okay? And then and if I call your name, you tell me your age, okay? That would also be a random variable, because what we're doing is it's a random event, and that's just I'm selecting a student at random. But the thing that I'm getting is not the actual student itself, but I'm getting the age of the student, okay? And that's a number, that's a random variable, okay? Or it could be maybe not the age, maybe it's the height of the student, okay? A random variable. So these could be illustrated several ways. So if it was a coin flip, the outcomes are 0 or 1, okay? So this is a number of heads seen. Alright, and the probability of seeing 0 is 0.5. So this is a number line, this is at 0.5. And the probability of seeing 1 head is also 0.5. We can make a frequency table, or I'm sorry, this is not a frequency table, this is a probability table. Okay. And the outcome, which we list off as y, y can be, after one coin flip you see 0 head or 1 head, and the probability of y here is 0.5, and the probability of y here is 0.5. Okay. Alright. And if we did a die roll, maybe the outcome, I'm sorry, y is the different outcomes. We can see 1, 2, 3, 4, 5, or 6. And the probability that we get this particular outcome is 1 out of 6, 1 out of 6, 1 out of 6, 1 out of 6. If we're dealing with I don't know. Okay, so if we did the classroom example, and let's say y is equal to height of a student. This might be a lot tougher. Okay, so I'm just going to make up some numbers here. All right, so we'll say somebody, let's say 2 out of 25 are 60 inches tall, and maybe 0 or whatever. Okay, it's harder to do, so something. Okay, but okay, we could create a probability tree, or not probability tree. I'm sorry, probability table showing all the possible outcomes of y and the probability of getting that particular value. Okay. So let's try something simple. So somebody might say, well, what is the average number you would expect from this random variable? Okay, there we are asking for the mean. So the mean of a random variable. Well, we would write this is y bar, oh not y bar, this is, we call this mu. Alright, when it's a random variable, the mean of a random variable is the Greek letter mu. It looks kind of like the letter U with a line in the front. It's actually the Greek letter for M. Okay, it's the Greek equivalent of M. But M for mean, it's mu here. Okay, and for a discrete random variable, this is equal to we multiply each value, the probability of y, times the actual value y. And I might have written this backwards, yeah, from what the book has. Actually, the book switches this y times the probability of y. I hope that's not too confusing. Okay?
And that's the sum of all the.
Sum of all the different outcomes.
Okay.
Okay? So for the coin flips, if I flip a coin once, what's the average number of heads I expect to see?
0.5.
Yeah, I expect to see half a head. Now, that sounds funny, but so let's do the example for the coin flip. What is the average or the mean number of heads I expect to see? Number of heads. Okay, well, we will do this, and we will say mu is equal to the sum of, I'll write it the way the book writes it, y times the probability of y, which in our case, y is 0, and I multiply it by the probability of getting 0, which is 0.5, plus y can also be 1, and I multiply it by the probability of getting 1, which is 0.5, and this equals 0.5. So my mean mu is 0.5. That says if I flip a coin, the number of heads I expect to see is 1/2. I expect to see half a head. That doesn't quite make sense, but it does.
Wait,
All right.
What's the 0 from?
Yeah, so what are my outcomes? I can
sure,
either see
okay.
0 heads or 1 head.
Okay, I
I
got
see
it.
0 with probability of 0.5, and I see 1 head with probability of 0.5. So I have to include all of these outcomes, and I do 0 times 0.5 plus 1 times 0.5, and I get this. What am I saying? So this is the number of heads I expect to see. And so, of course, when I flip a coin, I will never actually see half a head. I'm either going to see 1 or I'm going to see 0. But if I flipped a coin and I kept track of how many heads I saw, and I did this for a long time, and then I took an average, that number should be close to 0.5. That's what we're doing. Okay? That's what we're doing. So I expect to see, 0.5 heads. Okay? But of course, we will never actually see 0.5 heads. It's just in the long run, that's what I'm expecting. Okay. So let's try something not so simple. I mean, that just seems kind of silly. Okay, so the book, we have an example, and it says, apparently for a certain species of fish, okay, they're born with a certain number of vertebrae in their, I guess in their, whatever, spine, okay, on the fish. And so, I'm just going to make up different numbers from what the book says. Okay, so the number of vertebrae can be, let's say, 20, 21, 22, or 23. And let's say the probability, so y is the number of vertebrae, and let's say the probability that a fish has 20 is 10%, and let's say 70% of fish have 21, and 15 and 5. Alright, so what is the average number of vertebrae that a fish has? Let me just make sure this, before I say these are the numbers, just because I hate if the same stupid thing happened again with coincidentally I get the number that I don't want to get.
Does that say Y number of vertebrae?
No, y is my random variable,
Oh, okay.
which is the number of vertebrae. Okay, so it does say y number of vertebrae, but y is the random variable, which represents the number of vertebrae, and this is the probability that I get that number of vertebrae. And I think these add up to 100%, right? 20, yeah, 9, okay, good. So total. So the probability of getting a fish with 21 vertebrae is 70%. The probability of getting a fish with 23 vertebrae is 5%. What is the average number of vertebrae? Okay, so the mean number of vertebrae. Do we get an answer? What'd you get?
21.15.
21.15. That is our number. That is our mean. That is our mu. Okay? And this we found by doing, okay, well, what's the probability? Some fish have 20 vertebrae, and the probability that that one has 20 vertebrae is 10%. Some fish have 21. I multiply that by 0.7. Some have 22, and I multiply that by 0.15. And some have 23. And I multiply that by 0.05. And when I do that, I get 21.15. Okay. Notice, if I just said, oh, there's 4 types of fish, some have 21, some have 22, some have 23, and some have 24, and if I just said, oh, well, to get the average there, I just add up 4 numbers and I divide by 4, I would not get the right answer, okay? If I did that, 20 plus 21 plus 22 plus 23 divided by 4, this would give me 21.5, okay? This is not the mean. In fact, this number has no meaningful application to this situation. This is just the wrong answer, okay? I'm sorry?
No, because most of them are in the 21 here.
Yeah, because most fish have 21, right? So to add them up and divide by 4, that says each fish, each number of vertebrae is kind of equally likely to appear. And that's not the case. We're much more likely to see fish with only 21 than we are seeing fish with 23. Okay. So that's how we get the mean. All right. And if people ask, well, we can also get the standard deviation. Okay. And the standard deviation is kind of like, what's the average distance from the mean now? Okay. So let's get the standard deviation. So when we're dealing with a random variable, the standard deviation is symbolized by the Greek letter sigma. Okay, sometimes people write sigma this way, and this is the Greek letter for s. Okay, I guess you can kind of see it if you write it s with a, I don't know. Okay, but it's an s. All right, but it's a sigma. It looks kind of like that. For standard deviation, and we find this, okay, similar to what we did for finding the standard deviation by hand. We're taking the difference from each point from the mean. Okay, so I'm going to do y minus the mean. So that's going to give me the distance from the mean, and I square that distance. So just like we did for standard deviation. Okay, but instead of adding them up and dividing by n minus 1 or whatever we did there, okay, so instead of adding up and dividing by how many I have, I'm going to multiply it by the probability of getting this. I'm going to multiply it by either 10% or 70 or whatever it is. Okay, and so when I do this, and I do this for all of them, so I sum them up, this is going to give me sigma squared. Do we have a name for this? The variation. The variation is the standard deviation squared. So this is the variation. And then if I just take the square root of that, it gives me sigma. That's going to be my standard deviation. So don't forget to take the square root. Okay, so let's figure out the standard deviation for this set of numbers, okay? So the first thing, I've got to find the mean first, right? I can't do any of this without knowing what mu is. But I did, and I got mu is 21.15. So for each one, I'm going to say subtract off the mean, 21.15, and I'm going to square that difference. And I'm going to say, oh, this point is this far away from the mean, and I squared it. And I multiply it by the probability of getting that. So I multiply that by 10%. And then I add this, I do this for all of my values. So I have 21 minus 21.15. I square it and I multiply it by 70%. And then 1.5 times 22 minus see this can end up to be kind of tedious, but not impossible. Not impossible. Alright, so this will give me my variance. Remember, this is the variance. Here I get 0.4275. I don't know if you guys got the same number as I did. Maybe I made a mistake. And I get my standard deviation to be 0.6538. Something like that. Did we get this, or did you not even bother trying? Alright, okay, well that's how we get the mean and the standard deviation for a random variable. Is that alright? Okay, good, because now we are going to do everything and throw it all together in the binomial distribution. Alright. So the binomial distribution is a particular type of random variable. And here it's the outcome to a question where you say, well, if I tried this same thing several times, what's the probability that I succeed this many times? Okay? So if I do, so that I guess the general form is, if I attempt n trials of a random event, what is the probability it succeeds y times? Okay. And the word success or succeed is an arbitrary label that we've stuck on this thing. Not necessarily success in the classic sense of we feel victorious. So it could be as simple as, if I flip a coin 10 times, what's the probability that the coin lands heads exactly 4 times? Okay, so an example is, if I flip a coin 10 times, what is the probability that the coin lands heads exactly 4 times? It could be applied to any situation. So if you watch baseball, it could be if some player, so let's say if Yasiel Puig has 5 at-bats in a game, or what's the probability that he has 2 hits? Okay. Or if I look at 100 patients what's the probability that exactly 12 of them have high blood pressure or something like that? What is the probability that 12 or something like that, okay? Does that kind of make sense? So here, the requirements are, we have a few requirements before we can use binomial. So here is that for each trial, so each trial can only have two outcomes. Something happens or it doesn't. Something happens, which we label a success, or it doesn't, which we label as a failure, okay? But again, success and failure sounds so dramatic, but it's not, okay? Because it could be, and there again, the labels are arbitrary. So it could be if a family, if a couple decides to have 4 children, what's the probability that they get exactly 2 girls, okay? You're gonna have to label one of the 6, either girl or boy as a success and the other as a failure, okay? But that's not to say good or bad, it's just these are arbitrary labels in the, okay? Each trial has to be independent of each other. Okay, so going along with that is that the probability of a success remains the same for all trials. Okay. And we say, and this only applies with a set number of trials, okay? Number of trials is set. So number of trials is set to n. Okay? So every binomial problem, you need to be able to identify 3 numbers, okay? Okay? N is the number of trials. P is the probability of a success. And J, or sometimes Y, or depending on your book, it might be K, J, K, or Y, or whatever. Just some other letter. This is the number of successes that you are interested in. I don't know how. I'm sure there is, but I'm sorry, I don't know how. I can is it too cold or
I'm cold.
is that
A little chilly.
it's a little chilly?
Yeah, but it keeps you up.
Okay, keeps you up, yeah. I can call them and just request that they don't make it so cold.
Okay. Thank
So
you.
there's pros and cons to that, right? Sometimes they take it too extreme. Say, hey, you call this cold? Yeah. They're not vindictive like that, but sometimes I've called and then I'm like, oh, maybe a little bit of air would have been still good. All right. Requirements. Okay. So let's try this out. Let's try a simple example. And let's say if I flip a coin 3 times, what is the probability I get exactly 1 head? Okay. You guys can actually answer this question right now.
Point.
Hmm?
Okay.
So if I flip a coin 3 times, what's the probability that I get exactly 1 head?
0.5.
1.5.
No. Like I'm flipping it 3 times, right? So the coin can land heads what? 0 times, 1 time, 2 times, or 3 times, right?
Right.
So what's the probability that I get exactly 1 head?
0.5.
Did
All
you
right.
teach us anything today?
I know, you guys are breaking my heart. Okay, so let's just think about this, right? Okay, so I flip a coin 3 times. What are the outcomes? So possible outcomes are okay. Well, let's do this. Let's make a probability tree. All right. Okay. First coin flip can go heads or tails. Okay. Now, what's the probability it goes heads? 0.5, 0.5. Okay, the second coin flip. Here, what? Again, heads or tails? 0.5, 0.5. And then the third coin flip, also heads or tails. I get 0.5, 0.5. Okay, I'm gonna just go rapid mode because
But doesn't this mean that they're dependent?
no.
I thought the tree meant that they're dependent.
The tree doesn't mean that they're dependent. The tree is a tool that we can use when things are dependent, but they can also be used for when they are independent. Now, what's our biggest clue that this is still independent?
You flip it 3 times.
The probability of getting heads stays the same no matter what happened before it. Okay, so the probability of heads is still 0.5 here, as it is here, as it is here. Okay, if it were dependent, then the probability here would be different than it would be down here, right? The probability, so heads and tails are 0.5, 0.5 up there. They're also 0.5, 0.5 down here. Okay. All right, so here I've listed off all the possible outcomes, which is heads, heads, heads. Okay, those are all the possible outcomes that can happen when you flip a coin 3 times. And in which of these do I get exactly 1 head? This one, and this one. Can we see that?
Mhm.
And so, and the probability of getting this exact sequence is 0.5 times 0.5 times 0.5, that's 0.125, and this one's also 0.125, and this one's 0.125. So the probability of getting exactly one head after 3 coin flips is equal to 3 times 0.125 0.375. Is that okay? What's the probability of getting exactly one tail?
Same, isn't it?
0.375. What's the probability I get exactly 2 heads?
That's the same.
0.375, right?
Oh,
Because the
I see.
probability of getting 2 heads is the exact same thing as the probability of getting one tail. Okay?
Yeah.
Alright? Not trying to be tricky here, but
You succeed.
you just have to think about some of these things, okay? So probability of exactly one tail is also 0.375. Probability of exactly 2 tails, also 0.375, okay? Because 2 tails is the same thing as one head, okay? And so on and so forth, alright? What's the probability of getting 3 heads?
0.125.
0.125. That's this one right here. Is this hard?
No,
Okay.
I was gonna say it and I chickened out.
You got it. No. You know what? The worst thing that could absolutely happen is you say something
And
and
it's
you're
not
wrong.
right.
Yeah, that's
That is the worst thing that could possibly happen.
that is true.
Depending
That
on the
is-
circle you're in.
Okay. What if I found this mysterious coin, alright? I don't know if anybody's ever found one of these, but what if I find a coin and it doesn't land heads 50% of the time, but rather it lands heads 80% of the time?
And everything would be changed to 0.8.
Yeah, everything would be different, right? So let's say that what if the coin lands heads 0.8. Just make sure I'm okay on time. Yikes. Okay. Alright, so let's just say what's the probability of getting exactly one head? Okay, well the answer here is going to be different, right? Because now all of these are 0.8 and these are all 0.2. Okay? Okay. So these are all 0.8 and 0.2. These are still the answers that I'm going for. These are the ones that have exactly one head. Okay, so this one requires 0.8, then 0.2, and then 0.2. And this one goes 0.2, 0.8, 0.2. You might have to redraw your tree, and I apologize. 0.2, 0.2, 0.8.
But each one would be the same.
Yeah, we noticed that, right? Because here, the probability of getting heads, tails, tails is going to be 0.8 times 0.2 times 0.2. Alright? And here I got tails, heads, tails. That's going to be 0.2 times 0.8 times 0.2. And this one is going to be 0.2 times 0.2 times 0.8. Okay? So all of these, I'm multiplying a 0.2 in there twice and a 0.8 in there once. So this, I can rewrite the answer. My answer to this thing is going to be 3 times 0.8 times 0.2 squared. Can we see that?
Yes.
Okay. So we're going to use this this idea here, okay? What if, so that's going to be my answer here. Probability of getting exactly one head is going to be 3 times 0.8 times 0.2 squared. Okay. What if I said, what's the probability of getting exactly 2 heads? What do you think your answer there will be?
3 times 0.8 squared times 0.2.
3 times 0.8 squared times 0.2. Can we see that? Because I'm going to have to get 2 heads and 1 tail.
Right.
Okay? And then the 3 comes because there's 3 arrangements of these. Alright? So, I could make this harder, or not harder, but just more tedious if I said, okay, now we're going to flip the coin 10 times. Okay, what is the probability I get 7 heads, okay? And let's assume that the probability of heads is still 0.8. Okay. Well, we can try to make a tree, but we don't want to do that, because if we did the tree, at the end of this we're going to have 2 to the 10 or 1,024 different little branches to go and count up, okay? And that would be quite miserable, and I'm not that mean. Okay, but if I'm flipping a coin 10 times and I'm going to see 7 heads, how many tails am I going to see? 3 of them, right? So part of my answer is going to be 0.8, which is the probability of getting a head, and how many of those am I going to see?
7.
7 of them. And then what's the probability that I'm going to see a tail?
3. Or
0.2, right?
Yeah.
And I'm going to have at least 3 of those. The only thing I'm missing here is over here we said there's 3 of these.
10 times.
Okay? So here, this is, the 3 comes from how many arrangements are there where I flip a coin 3 times and get 1 head, okay? This is known as the binomial coefficient, okay? There's the binomial coefficient. This can be rewritten as n choose j, or n choose j like this. Sometimes we see it. So there's this number that this thing represents. It says if I flip a coin 10 times, how many ways can I get it so that 7 of them are heads? Okay, and that's what this thing does. Okay, you can. There's a formula in the book. Don't worry about it. We're not going to worry about where this thing comes from. We're just going to say this thing exists. Okay, you can use a calculator to find it, and if you on your calculator you might have a button that says NCR. So your calculator, you might write 10, and then you hit the NCR button, and you hit 7, and then you hit equals on your calculator. You might have to hit like shift something to get NCR. If you don't have that, maybe on your calculator you have a PRB button for probability, or maybe there's a math button, and then you use the arrow keys, and you pick the NCR command. Alright? And then you're going to do 10 and then NCR 7. And you're going to do that. Okay? So when you do this on your calculator, oops, I get 120. 120 here. Okay? So this thing is equal to 120. Where do we go? So that says 10 choose 7 is equal to 120. And that means if I flip a coin 10 times, there's 120 different arrangements where 7 of them are going to be heads, right? Because it could be all 7 in the beginning are heads. 1, 2, 3, 4, 5, 6, 7, and then I get tails, tails, tails. But then I could also get tails, something like that, right? And you know, I could list them all off. I probably can't actually. There's 120. Okay, there's 120 of them. Okay, that's what this 10 choose 7 means. It's kind of neat how we get there, but we're gonna run out of time if I try to explain that. So we have that thing. You can use your calculator. There's also, if you don't have a nice little calculator, you can use the formula in the book, which really only works if you have a nice calculator because it requires the factorial. But there's also a table in the back of the book, I think table 2, and you just kind of look up 10 and 7 in the table, and at in the table it'll tell you 120. Okay. So anyway, the answer to the question then is going to be 120 times 0.8 to the 7 and 0.2 to the 3. Is that okay?
Yes.
We got this? All right. And so the overall, the formula for this, okay, is that if you have your n and your p and your j or whatever it is, okay, you do n trials, and each trial has probability p with success j, and you're looking for j successes. The probability that that you get j successes, okay, so that the answer to the question, if I do this n trials, what's the probability that I get this many successes? So the probability of having j successes is equal to n choose j times p, which is the probability of a success. You need j of those, okay? And that means you need how many failures? You're going to have n minus j failures, right? If you flip a coin 10 times and you have 7 heads, how many tails are you going to see? You're going to have 3 of them. And then what's the probability of a failure? 1 minus p. Okay, and so that's how we get this binomial equation here, or binomial probability.
You said not to worry about that part, right?
Not to worry about what part?
You said not to worry about that, or we do need to.
No, you do need to know. You do need to know all of this, okay? Sorry.
That's okay.
I know. Alright, and the last bit, okay, and I know you guys are dying to get out of here. Okay, so the last bit is we could create a probability table. So if I said, okay, I flipped the coin 10 times, alright, and y represents the number of heads. And I could use this thing to get the probability of what? Well, if I flip the coin 10 times, I could get anywhere from 0 all the way up to 10 heads, right? Y could be any value from 0 to 10, and each of these will have a value, right? This first one is going to be 10 choose 0 times p to the 0 times 1 minus p to the n minus 0, so 10. And I could do this and I can get all of these, and this is going to be 10 choose 1, p to the 1, 1 minus p to the 9, and I do this for every single one, okay? And then this is just like a random variable, and I can ask for what's the mean and what's the standard deviation, okay? Now, you could do the same thing where you do that formula, y times the probability of y, and you add them all up, okay? Well, it turns out there's a shortcut, okay? If I ask for what the mean is equal to n times p. It's a lot easier than trying to do this whole thing, right? And this makes sense, right? If you do something n times and the probability of success is p, overall you'd expect n times p. So if I flip a coin 10 times and the probability that it lands heads is 0.5, after 10 coin flips I would expect 5 heads. That's what this says. And then the standard deviation okay, I don't expect you to get this on your own, is n times p times 1 minus p, okay? And again, if you use the whole random variable table method, you would get that same exact answer, but these are shortcuts that give you the mean and the standard deviation. I think a lot easier and a lot faster. Okay, so that is ends our time together. We'll see you guys next week. There's some information about the quiz that we'll see next week posted.